This is the second of our annual 3 lectures in the series Astronomy for the Public. It's part of a series which has been going on for 11 years now, and it was a national program originally called PEST, Public Education and Engagement in Science and Technology. And that's a bit of an unfortunate name, so they changed it and called it the Public Understanding of Science. Not necessarily the best acronym there either. So from our point of view, we call it the Green Templeton College series on astronomy for the public, and you're all very welcome. I assume at least half of you are professional astronomers. I hope that at least some of the rest of you are also artists and designers. Because tonight our speaker, we're very privileged to have Professor Jayanne English from Manitoba, who's trained in both art and design and science, in particular the science of astronomy, with a PhD therein. She's going to talk tonight to us about the merger or the closeness of the two, art and science. Jayanne.
Thank you. Thank you very much. Thanks for coming to attend this talk, and it's going to be presented, as Jeff said, from someone who trained as an artist, who's an astronomer. And what we're going to talk about is public outreach images. So sometimes when I talk about public outreach images, I talk about it in terms of a battle between the culture of science and the culture of art. Public outreach is an informal education, and the International Astronomical Union has noted that it's really important not just for media people to do, but for professional research astronomers to do as well. So they say as our world grows ever more complex and the pace of scientific discovery and technology change quickens, the global community, the international community of professional astronomers needs to communicate more effectively with the public. And the reason for this is that public outreach has really high impact. In the International Year of Astronomy in 2009, in Canada, where we only have 34 million people, 2 million people self-reported that they had an experience with astronomy, going to lectures, planetaria, looking through telescopes. So that's quite, especially since a lot of people didn't report, that's a lot of people who had an experience with astronomy. Also, they learned that politically there's a very strong impact. The head of NASA at one point decided there weren't going to be any more servicing missions for the Hubble Space Telescope. So in the middle here we have the Hubble Space Telescope. I'll also refer to it in the talk as HST. And they weren't going to service it, but there had been so much informal education, public outreach about this telescope, that the American public said, you told us this was the best telescope in the world. How can you not service this telescope? Indeed, the head of NASA lost his job over that, and they reinstated servicing missions. So it does have a strong role to play. And also, it's permeating our culture now. Here's an example of clothing with Hubble Space Telescope imagery on it. You've seen backpacks, there are carpets, there's mugs, there's all sorts of things for your home. So it's permeating culture as well. So public outreach images are those that were going out into the public domain, mainly in the form of textbooks, newspapers, and magazines, but now they're all over the internet. There are databases that are galleries of images. There's the Worldwide Telescope and Google Sky have public outreach images. There's all sorts of video podcasts that have the images. So there's a lot of places that these images can now be disseminated. And again, we want to know what the intention of the people who are making the images, what is their intention. And I worked on a project called the Hubble Heritage Team, which made pictures from the Hubble Space Telescope. We need some lights so that you can see me. I'm going to make it darker when we need to have it darker. So don't worry, I'm going to say I want it dark now. Okay, so by emphasizing compelling Hubble Space Telescope images distilled from scientific data, We hope to pique the curiosity about our astrophysical understanding of the universe that we all inhabit. Now, this is written by astronomers, and so the astronomers want to build bridges between themselves and the rest of society. The images are not supposed to tell you scientifically everything about the object when you look at it. It's supposed to inspire you to go to all of those places on the web and find out more about the astronomical target or phenomenon that's in the images. So who are the people that make these images? Well, one of my favorite examples is a lone photographer named David Malin at the Anglo-Australian Observatory. This is a picture of him from the 1970s. And he was hired as a research photographer to develop methods for astronomical research, but also the director of the telescope gave him time so he could take images and they would be appropriate for textbooks and newspapers and magazines. Today we don't work alone, we work in teams, and one of the first teams was the Hubble Heritage team that I've already mentioned. And this team collected data from the archive for the Hubble Space Telescope, and we made images. And look, there's quite a lot of us. And you can recognize me because I'm the short one. Then that led to astronomers working with their colleagues. And so what happens is we will go and collect data, say at a radio telescope like this one. This telescope is in British Columbia, Canada. It's called the Dominion Radio Astrophysical Observatory. I might refer to it as DRAO. That's our affectionate name for it. There's two of my colleagues. Whenever we do a research paper, we would also produce public outreach images. Another fellow that does this is named Travis Rector. How many of you are citizen scientists? Amateur astronomers? Yeah, amateur astronomers in the group? A few. Okay, so you guys are doing great work as well. Okay, so that's the example there. And the equipment now for the hobby scientist is really good, and you have the time to focus on a target. And we have to share the telescopes with all our other colleagues. So these citizen scientists can do some really good detailed work that can contribute to research. So they've started to contribute to scientific papers. And then the archives for telescopes have opened up, and occasionally there's a competition, and the general public can go and make images the way the Hubble Heritage team did. But what I'm going to focus on are the research astronomers. Now, the public wants to know, these images, are they fanciful spacescapes? Are they snapshots? If you could put your eye to the Hubble Space Telescope, is this what you would see? And editors, especially of newspapers and magazines, really would like this to be what you could see with your eye, be convincing and compelling. This tradition of making really naturalistic, convincing images is called the Western image tradition of representation. Right up here, image tradition. So I'm going to refer to image tradition over and over again. They mimic nature. They appear to preserve the form of things as they would occur in the world. If you want to prove that something's happening, then you might make something really look realistic, like this one. And it can prove that an event is going on. But these images are constructed out of data. So what's the data tell us? We might want to have this dark for a minute so they can see this image. Look, can we have it? How's that? That's good? Okay, now we can turn it back on. Okay, so galaxies, these are dwarf little galaxies. They're in an area that's smaller than the radius of our Milky Way galaxy, and they feel the gravitational tug on each other. And this causes them to have peculiar features, like this one here, which is its gravitational pull on the stars and gas in this galaxy. And when these galaxies feel the gravitational pull, they orbit around each other closer and closer and finally merge together and form a new galaxy. And as they do this, the gas in the galaxies flows, compresses, and it starts stars to form. So here we have stars forming, nice glowing gas heated up by stars. It looks pink. And here are fresh young stars. They're blue here. They're young stars. And what we wanted to know is there an example in the nearby universe of galaxies that are merging together to form a new galaxy that we can look at? Because if we want to look into the past, into the early times in the galaxy and see how, in the universe, and see how galaxies formed, those galaxies to us just look like blobs when they're far away. So if we can find an example nearby, then we can study that and learn how galaxies formed in the past. And fortunately, this system, the stars are actually, in astronomy terms, really young compared to the universe. So yes, we can study that nearby. So that's what we're getting out of the data here. And these images are constructed out of data. But the data, these kinds of images, aren't image tradition representations. Instead, they're logic tradition representations. And here's a quote about what a logic tradition representation is. What you used were counting rather than picturing machines that aggregate masses of data to make statistical arguments for the existence of a particle or an effect. In other words, you're going to be counting and you use mathematics. Now, in your cell phone or your iPad, you have a camera. That camera is the same kind of camera as on the Hubble Space Telescope, a CCD camera. And each pixel in that camera is counting the number of light particles, photons. Okay? So there we are. We have a logic tradition image where there's counting. And what we do is we take different exposures of the same target and we combine them together mathematically. So there we're using math. But I think what's really the best example of a logic tradition image is that comes from radio telescopes. So here's a picture I took of the Anglo-Australian telescope. And we have a bunch of antennas on the railway track. And what happens is as the Earth turns, you can see it makes a circle. And that circle can be mathematically synthesized into a mirror. So for the first part of that turn, you don't have very much data and you don't have an image. But eventually, in the logic tradition, pictures become surfaces on which quantitative information is deposited. So over 12 hours, that's what's going to happen. Here we go. We circle the Earth, and right in the center here, we have a supernova remnant. So these rings are artifacts. A supernova remnant happens when you have a massive star, and that massive star explodes, and the remnant material is called a supernova remnant from that explosion. Okay, so the images made by professional astronomers are embedded in this culture of science. We really like the culture of science. We like knowledge. We like to show our knowledge in the form, usually, of contour plots. And when we think that our knowledge is made very clear, you can tell which parts are hotter than other parts in this image, then we think that's a beautiful image. But it just looks like blobs to the public. And they're not intrigued at all. So what we do is we use visual art techniques, if we're an image maker, to make the images more interesting for the public. And this is the same target as this one that you've just been looking at. Okay? Big difference there. Okay, so we'll do that once more. Okay, so I'm going to take you now through a little tour of one object. It's a supernova remnant called the Crab Nebula. And this is kind of a historic overview about public outreach imaging projects. And I mentioned in the beginning about David Malin, and David Malin made images like this one. So this is a Crab Nebula, and what he did was something, he actually set up the method, the approach of how we make images. We still use his approach today. And what he was able to do was take the filters that we're going to learn about shortly and the film and select different parts of the light that we see so that it mimicked what our eyes would see. Now the problem is that our eyes do not respond very well to only a few photons. We don't see color then. So we have to have eyes that are as sensitive as photographic film to see this. But if we had eyes that were that sensitive, this is almost what your eye would see. So if anybody asks you, if I look at the pictures, will I see what my eye sees? You can say, only if you look at David Malin's pictures, okay, from the Anglo-Australian Observatory. Now we're going to focus in on some of these filaments here and look at it from the Hubble Space Telescope. Oh, okay. That's what it looks like. This is by a scientist, and what offices of public outreach used to do was appropriate what scientists had produced for their own insight and communication with their fellow scientists. The science is really important to Bill Blair here, who took this data, and he says, see how the faint blue gas seems to envelop other colors? That tells us that the hotter, low-density gas surrounds the denser, clumpier gas. Are you guys lost? I'm lost. An editor of a newspaper is going to strip this off. You won't know what the splotches mean. But what's really important to the scientist is the scientific meaning and not the aesthetic. So the Hubble Heritage team came along, and they used data from the same project, and this is the kind of image they made from it. And we don't lose the scientific information. These different colors tell you the different elements. For example, this green here, oxygen glows green. Okay, so that tells you that's oxygen. The pink is hydrogen, just like it was in David Malin's image. And here's a pulsar, and there's a wind coming off the pulsar. So we have scientific content here, but the aesthetic is important to us as well, and they're balanced. Okay, so how do we turn our data from logic tradition representations into Western image tradition representations? So for the data, we're going to sample it in the electromagnetic spectrum. And here you can see in the electromagnetic spectrum that what we see with our eyes is really tiny. So I'm going to call this the optical regime. And you can see as you go to the left that there's higher and higher energies, and that's to the blue side of our optical part of the spectrum. Infrared and radio are to the red side of that spectrum. And there's infrared, microwave, radio. We can think of light in terms of particles, or we can think of light in terms of as a wave. So if it's a wave, it'll look like this. And we have infrared, microwave, radio. And what you'll notice is the distance between these peaks changes, and that's called the wavelength. So the distance between the peaks is the wavelength. And the longer the wavelength, the lower the energy, and we refer to it as red. And the shorter the wavelengths, then the higher the energy, and we refer to that as blue. So try and keep that in mind. And how we make the images is we set up filters, and all of those wavelengths come in towards the filter, but the filter only passes a certain small segment of the electromagnetic spectrum. Okay? So all of the colors come in and only yellow is passed here. So if we take images of an object at different wavelengths, this is the sort of thing we get. Over here we're looking at, in astronomy, there's so few photons, we devote all of our hardware to capturing those photons and none of it to encoding color. Okay? So we get black and white images. And the black and white images for the low energies show you the cooler, older stars. For the ultraviolet, you're going to be looking at gas and stars that are young and hot. But what I want you to notice here is how little of the optical wavelength range is sampled. There's only 2 filters there for this, and none of these we would see with our eyes. So what we have to do is take these black and white images and assign color to them. And when we do that, we can get an image that looks like this one that shows us the cooler, older stars are in the center, surrounded by a ring of dust, and young stars are forming in this ring. I'm going to show you here an example of how we create these color images. We use a metaphor called layering in some manipulation package. So what we have here are these black and white images. They're going to assign colors now to them. And I'm going to turn them all off. It's like they're on transparencies, and you can see them through each of them. And I'm going to colorize one of them red. And then I'm going to turn off the black and white. And then I'm going to go to this wavelength range and color it green. And then the high energy wavelength range and color it blue. And that's an example of how we start to colorize our images. And we can make up names about how we're going to colorize them so we can communicate with our colleagues. And if we do them in that order, where we go from high energy is blue to lower energy being red, we call that chromatic order. But we might mix those up. Maybe colorize the high energy one green in the middle. And I want you to keep in mind, why would we even ever want to do that? Keep that question in mind. Here are some filters from the Canada-France-Hawaii telescope. And I'm showing you this because I'm going to point out to you what we see with our eye and what the telescope sees. Now remember, we're taking black and white images. And for the black and white images, for this filter, so it's blocking all of the other wavelengths and it's just letting photons in through this filter here. It goes from, I'm going to convert this to nanometers, so 400 nanometers to 600 nanometers. Okay, 400 nanometers to 600 nanometers. That's our black and white image. Now, this is a color space. This is a mathematical space that's used for studies of human color perception. And what you see here is down here is 460 nanometers. So 400 nanometers is even off of the plot. We don't see it. Right through to 600 nanometers, goes all the way over here. 600, it's orange. So through that filter, all those photons are all the colors we see. Here at 500, on a different data projector, you'll see green. Here at 500, we're green, and all the way over here at 600, we're orange. All the colors we see except red are in that one filter. How are we going to colorize it? Well, we often say, well, we're just going to take the middle color, which is green, and we're going to colorize it green. But we don't have color information that goes with our eyes. Okay, so this is from the CIE Institute. So when we have images like this, I just showed you how we might assign color to these ones. But what do we do about these images here? What you'll see is that these two images look very different from each other, but they're all just past the 600 nanometers. So they're in the red. This one would be red to our eyes. This one would be red to our eyes. But they're very different. The star cluster doesn't show up much there. And there's all this filamental structure here. So if we colored them the same, we would lose the information about different elements in this nebula. This is hydrogen. This is sulfur. Over here is oxygen. Do you remember what color that was? Green. Great. Okay. So that's how we would color the ones to get a nice balance for the stars. And what we're going to do now is use this opportunity to use techniques from art. So our coloring isn't going to be arbitrary, but it's going to be informed by what happens for human perception. And I want to show you something about visual grammar. In visual grammar, it's about how you read and construct an image, the elements you use. And the elements you use are techniques of composition and color harmony. And what this does for you is it engages the viewer because using techniques from art, you can create spatial depth, you can create a richness in color, and sometimes you can retain some of the information that gets stripped off by an editor because they don't like those captions. So, if you want to know how to do this in detail, you can rewatch this lecture on Voices from Oxford. So thank you to Voices from Oxford for videotaping this. If you want to know how to do it hands-on, contact me. I'm going to organize some workshops in the Trinity term. And there's a lot of YouTube videos. And I want to prove to you, first off, how important color is to human beings. So I'm going to ask for the lights to come off. And what we're going to do is we're going to look at the circle on the right-hand side. And then after 15 seconds, we're going to look over here. Okay, at this little black ring. Okay, I'm going to count. I want you to look at it. I don't want you to think about it. I want you to open your eyes and look at that yellow circle. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. Don't look away. 7,000, 8,000, 9,000. 9 3/4, 10, 9 3/4, 10, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 3/4, 9 11, 12, 13, 14, 15. What color do you see when you look at that black ring? Blue. And nobody came and painted the screen, right? Okay? So, if you want to turn the lights on, our physiology demands that we see another color. And that color we refer to as a complementary color. That's not flattery, it's the other half of something, okay? So that's a complementary color. And you can make images that work with your eye-brain system that produces color like that, or you could ignore it. So I'm going to propose that we use our eye-brain system and work with it. And a handy way to do that is to use these color wheels. And for the color wheel, that blue-violet is opposite from the yellow, right? And if you do the same thing with cyan, you'll see a red-orange. And for green, you will see magenta, okay? If you're using a computer to make your images, then you know that we refer to these primary colors that you build up all the other colors from as RGB. But that R is really that red-orange, and the B is really that blue-violet. Okay, and that's how you can tell. If you look at it in terms of nanometers, the wavelengths, you'll know that it's blue-violet. If you use pigments and you take the complementary colors and you mix them together, your eye will perceive gray or black. If you use the monitor and you mix together, you put together the complements, they will mix together so that you perceive white. Okay? That's how you know you have a complementary color, is because you will get white. If you blow it and you're off, you're going to get brown, which is the least harmonious color you can make. Now, I've just not made a value judgment. It's a definition in art. If you can mix two colors together, like the complements, you have a harmonious image, color image. If you don't, then it's not harmonious. So, you know, I have to make images that have more than two colors, though, right? So, or start with my filters, I have more than two filters. So what I can do is go across the color wheel, and I can split this complement. I can move to equal number of degrees on either side, for example, to magenta and cyan, and form a triangle, an equilateral triangle in this case. And that will mean that if I mix the magenta and the cyan together, I'll get blue-violet, mix it together with the yellow, I get black or white, and hence I have a harmonious image. Another thing about the color wheel is mainly things that are to this side, the yellows and the reds, they're called by artists warm, and these blue colors are called cool. So you might want to keep that in mind as well. Okay, here's some of the elements for visual grammar. What happens is your eye, doesn't matter what culture you're in, your eye will come in the bottom left-hand part right here, about a fifth of the way up, and go out through the top right-hand corner. And if it does that, your brain goes, been there, done that, I don't have to look anymore. You're not engaged with the image. So what you do, the artists have figured out how to block the eye from going straight out that top corner. Van Gogh has put this dark vertical wall right here, and it slows you right down, but he draws you over to the moon, and you encounter this virtual diagonal here. This all happens within a matter of seconds, okay? And your eye goes up this diagonal to that star, slides down to that star, does another lap around here, and finally it's looking at the subject, which is down here. Notice how clear that subject is compared to anything else in the image. So you don't want to have something that looks like a bullseye that's static in the center, if that's what your area of interest is, because the mind goes, I know what a bullseye is, I don't want to look at it anymore. You want to put it off center. So he's put it off center, and these are the paths that you can use. This is just kind of like the nth path goes down there, the number, how many paths, maybe n number of paths, and that's kind of path that goes around in the image. Let me give you an astronomy example. Now we need the lights off again. And this, astronomers use maps that are north to the top and east to the left, because then when you put them over your head, you can match it up with the sky if your head has got north behind it. And that was devised by old white dead Greek guys, and if it happened in the southern hemisphere, it would be a different convention. Astronomers are quite wedded to it. When you look at this, these galaxies that are interacting with each other gravitationally, they look like two eggs in a frying pan. It looks really kind of flat. But if you rotate it 180 degrees, what happens is your eye comes in here, it encounters this virtual diagonal here, goes over to that star, so there's another star there, and starts circling around in this image. You start to see the detail here on the arm of the galaxy. It swings out, and you get a bit of spatial depth. Sometimes, is it working for you guys out there? Yeah. Sometimes when I give a talk, people don't believe it's the same image, so I'll go back and I'll show you that there's no cutting and pasting. Those are the real stars that were there, and here's the virtual diagonal, and all you had to do was rotate it. Okay? This image here, I'm going to point out not for its great composition, which stops your eye from going out the top, but because the color blue here is associated with ice and snow. We can have the lights up again. And the mud is warmer than ice, right? And it's colored red. So I want to ask you how the public is going to read this next image. What I'm going to show you is what our star is going to become when it dies. It's not going to become a supernova remnant. It's going to become something that has nothing to do with planets, but it's called a planetary nebula. So there's a planetary nebula. How many people think the public is going to think the blue part in the center here is cold? Yeah, the public's going to think it's cold, right? It's not. Astronomers made this image. And remember our beginning where we said high energies were blue? So the astronomers made the hot part blue. So the point of this is you can take the data and you can make different renditions. This was made to be pedagogical, to teach the public that blue is hot. But if you wanted them to read it right away as the central part being hot, which it is in a planetary nebula, that's where the core of the star is, it's very hot, and the outer layers in the outer part being illuminated by it, you could turn this into red and this into blue, and they would understand this image immediately. Okay, these circles are the identical size. Which one comes forward? Seems bigger. Red. Okay. So, by definition then, anything that comes forward to an artist is warm, and that goes back is cool. For a scientist, which one's hot? Blue. Okay. So it's opposite to what artists call it, right? Opposite. Okay, so now this is going to give us an idea about how to colorize these last three images of sulfur, hydrogen, and oxygen. If you want to create spatial depth and you want to have that star cluster popping forward, you want to use a cooler color to go back and a warmer color for far away from the star cluster. And that's what we did. Here's our star cluster. The greens are cooler than this warm color over here. If we made this part, colored the data so that this part was magenta, then this would pop forward and we'd lose our spatial depth. You might have to have the lights off to get more spatial depth, or are you getting some spatial depth? Okay, there you go, right? Notice also that we have complementary colors. This is a harmonious image. We've got that magenta and green happening. So that's a harmonious image. Okay, we can leave it off for this one because now I'm going to say if you pick a whole bunch of colors and you make them dark, okay, you make them dark so that they're all the same dark intensity. Those are called, you can make either shades or tones. And then you add white to one color. That's called a tint. You can make something look like it's glowing. Okay? It's another bit of color magic that you can employ when you're making images. Now, if you're doing black and white pictures, so we can have the lights up again. If you're doing black and white images, then you only have one contrast. It's called light-dark contrast. When you're doing color, you have 7. You've got to work with 7 color contrasts. Okay, if you want to have something scream at the audience like advertisers do, you use pure hue, like the top one. If you are colorblind, you'd work with light-dark. We've already talked about warm-cool. We had an example there in the last nebula of complementary contrast. The one where we looked at the yellow dot, That's called simultaneous contrast, where you build the colors in the eye-brain system. And that's what the pointillists and the Impressionists and Van Gogh used. Again, if you're colorblind, you can use saturation, where you have an intense part surrounded by more dull colors. And you can also use areas and balance areas of colors. So I've given you an awful lot of art techniques, and you might think that we really manipulate the data and create these very fanciful spacescapes, but we don't. As research astronomers, we want to represent our organizations well, and we want the public to know that when they look at something like this, it's not a fanciful montage, but it's actually real. These galaxies are very peculiar because they're gravitationally interacting. So let's ask what we should be suspicious of when reading the newspaper about these images. If they say Hubble snaps images of, we know that it's logic tradition imaging. It's not a snapshot. The images, the data are collected over time. There's human intervention. It's not like a capturing in a moment of time without any intervention. If something says this true color Hubble Space Telescope, remember that we have all these filters that are outside of the range of what our eyes would see, and we only sample little bits of the range of wavelengths that our eyes do see. So it can't be true color. This begs the question, what would we see if we went up to the Hubble Space Telescope? Let's look at another planetary nebula here, and this is what we would see. It would be either gray or kind of a ghostly green. And if it's green, we'd look at it and we would say, oh my goodness, there's oxygen there because that glows green. But we also have spectrographs. And if we use a spectrograph, we find out that this planetary nebula actually has a lot of hydrogen in it. Not oxygen, but hydrogen. So as a research scientist, I'm going to colorize it according to that information. And what I get is a planetary nebula that's pink instead. And it's got cooler stars and hotter stars. These blue stars are hotter. So what we're trying to do here is show really that it's hydrogen and hot blue stars, and that it's what our color is telling us what is telling us what is physically going on. Okay, so we're true to the physical phenomenon as opposed to what our eyes would see. Okay. Here's something, I really like radio telescope data, because for radio telescope data, you don't have to worry about what the eye would see. Okay, it's just not there. So this one is from DREO and also from an infrared satellite called IRAS. And people think that these are really striking images, so they think that maybe they're artworks. And indeed, there's some cultural theorists who talk about them being in the romantic landscape tradition. People argue with her and say, no, they're from science fiction, book covers. Other people say, no, wait, this might not be art at all, because there's not one photographer taking the picture. It's made by teams. There's a lot of different software used. There's a lot of manipulation. But I think the person who has the best answer is James Elkins, who says there's no formal connection to concerns in contemporary painting or photography, and therefore they're not artworks. And I agree with him, and I'm going to show you some examples at the end of artworks instead. So what James Elkins like is that astronomy phenomena and the data are really complex, and they're even at the limits of our ability to represent them. And the data contains scientific results. So what I like to do is point out that what we're trying to do with the public outreach images is make something that will resonate with the science that we know. So we're making Western image tradition renderings that will resonate with the science that's in the logic tradition data. So in an image like this one, we will have these are supernova remnants here. They're yellow and red because the low energy radio, the lowest energy is actually colorized red. And this one here has got the lowest energy. That means it's a really old supernova remnant. The green can also be kind of a thin gas called a plasma. Okay, so what's really interesting for those who are interested in science here about these supernova remnants, they're emitting synchrotron radiation, and synchrotron radiation comes from when you have a charged particle, like an electron, spiraling around a magnetic field. So it's in conditions where you have both magnetic fields and charged particles. And that happens in supernova remnants, and in this gas over here, it's not happening. This is dust in the blues, where everything adds together to give white. Hello, I have a harmonious image. It added together to give white. Very pleased. These little clouds here, these clouds, if the conditions are right, they will collapse to form stars. So in this image, we actually have the cycle of star birth and star death. Now, if you look at these little dots here, you'll see that they're red and yellow. So they've got radio emission there, and the low energy radio emission. There's synchrotron as well. That means that there has to be magnetic fields there. And you might think they're stars, right? But they're not. They're quasi-stellar objects, quasars. Quasars are where you have a galaxy that has a black hole in the center, and that black hole, as material accretes on it, shoots out jets, and those jets have magnetic fields, and the particles in the magnetic fields create this radiation. So this image is also a quasar detecting machine. Okay, so let me tell you a bit about the jets. Here's some radio data, very blobby. The galaxy, it's an edge-on galaxy. It's forming very few stars. You're supposed to have these synchrotron halos around galaxies where there's magnetic fields and charged particles, only if you have a lot of stars forming. This one doesn't have very many stars forming, but it's got this huge halo. Well, we got better data from the Jansky VLA, and I'm going to show that to you. This is the disk of the galaxy. I made that out of 5 different telescope data. And then the radio data from the VLA looks like this. There's the disk of this galaxy, and look at that. This is the jet I'm talking about. There's a quasar, and there's the jet coming out of it, very large. It's way in the distant background. And this disk of a galaxy is in the foreground. And what we got fooled by was that background galaxy with the jets is almost dead center and perpendicular to the foreground galaxy. So we called this nature pulls a fast one. You can also look at expanding shells, and when you have an expanding shell, the material that's coming towards you is coming fast towards you like that, so it should look like it's popping towards you. It's also, how many people know Doppler shift? Okay, we're going to do Doppler shift. You've probably seen it on Big Bang when Sheldon dresses up as the Doppler shift and he goes, meow, right? So something that's coming towards you goes, and as it goes away, it goes, oh. And it happens for light too, and it's got to be along your line of sight. So when this shell is expanding, the material that's coming right at you is going to have higher frequencies, shorter wavelengths. That was blue, right? So we call it blue shifted. So we have blue shifted material, and this is a bluer red, and it looks like it's coming right at you. Here's another expanding shell. So this is showing you that we retain the scientific information in our images. This one has synchrotron emission, all this green stuff. It's not that it's bad data. What it is that our Milky Way galaxy is threaded with magnetic fields. Another supernova remnant, another jet back here. And let's zoom in here, supernova remnant. And then this is hot dust. Focus on this hot dust. There's a star cluster right there. And we look at it in hydrogen gas. Star clusters in here somewhere, hot dust in the pink. And this is evacuated, the cavity in the gas that's between the stars in our galaxy, because it's been heated up and it's escaping into our halo of our galaxy. But if you look here, we've got some warm colors, and over here we've got some bluer colors. So this is blue shifted towards us. So the galaxy is rotating. This side is going away, that side's coming towards us. So in this image, you actually have a sense of the rotation of our Milky Way galaxy. Okay, let's just look visually at this one. What part's coming towards you? Red? Blue? Red? Okay, so the projector's not helping me, right? But we saw before that it's the red that comes forward, right? Okay, so the red, it depends on the brightness of the projector, but this is brightening up, but the red usually comes forward visually. Okay, so this is a rotating galaxy. It's a bit messy. It's got a lot of hydrogen gas out in its arms, but it's rotating. And so the part that's coming towards you would be blue shifted, and the part that's going away is red shifted. So it would be going like that, but in this color map, it looks like it's going like that. We can change the color map from the one that's on the left to the one that's on the right, and it's a warmer blue. And that definitely comes forward now, right? And the red goes back. Okay, so we can change our color map, and now we see that this little cloud is flying towards us. And this little example is how our knowledge that we glean from doing public outreach images can feed back into our astronomy work. Now, the astronomy landscape is really changing. There's many more telescopes coming online, very exciting telescopes. I was just wanting to show you that a new frequency regime has opened up at very low frequencies. The VLA, this is the telescope that was used in the movie Contact. This one has been refurbished and much more sensitive. We're going to have a telescope called the Square Kilometre Array, and it's got some Pathfinder telescopes called ASCAP in Australia and Meerkat in South Africa. But the one that's my favorite at the moment, and unfortunately I don't have any images to show you from it, is ALMA. And it's in Chile. I'm up here at 5,000 meters. And it has the same resolution as the Hubble Space Telescope. And it's all serendipitous discovery at the moment. People say, we're going to find this. Other people say, we're going to find the opposite to that. They make both of them convincing arguments, and we don't know yet. It's all new frontier. So what are we going to do with all this data? Well, astronomers want to put data from different telescopes together. So we do comparison at multi-wavelengths, not focusing on just one telescope. This is putting together the halos of 30 different galaxies, those radio halos, the radio halos that have synchrotron emission, which is charged particles and magnetic fields. And remarkably, most galaxies have them. And this is to represent the disk of a galaxy. And this went into the publication, and all the scientists loved it, right? Nice, clear contour plot to them. But they would not put it out in the public. The public release office would not use it. They don't like contour plots. So we had to make another one that's in the Western image tradition of image making. And so we went and got one of the galaxies in our sample, and I made the Hubble Space Telescope image of it, and I had to mask it together using a more complicated technique. So we're going to have to change our techniques for astronomy image making to something more complicated as time goes on. And these kinds of images are really convincing, and we have to be careful about how convincing we make our images. Because if you look at this one, people have come up to me and said, LIGO, gravitational waves, fantastic, but what's even better is the photograph they've taken of the two black holes merging together. Okay. This is not a photograph of black holes merging together. We do a lot of now computational physics. So we build the universe in our computers, and then we look at it. And then we render it in the Western image tradition, which is very convincing, compelling, mimics how nature is. And we believe it. So we have to be careful about this. It's a rendering from a computer simulation, not the real universe. Now we can feed it back into astronomy and make ourselves little interactive tools. So when we do make computer models, we want to compare those computer models together. And I told you about if we use complementary colors and we put them together, they will mix together to give us white. So in this, I want to compare the data with the models, and one model is cyan, and as I move my mouse, the other orange model comes into it where they match up together. They're white, but where they keep their pure colors, you can see that they differ from each other. So we can rank our models, say which ones are better, which ones match the data better. And the big data sets coming from these telescopes now require there to be very novel methods. We're not quite sure what to use. And we're going to explore different avenues such as immersive 3D virtual reality. So I'm working with two people. We have a human-computer interaction lab in Manitoba. And color is going to be critically important for when we stick our galaxy data in the middle and put on our goggles that have head tracking. And we want to encode scientific information. So that's where we're going to go. For public outreach, I move also in a realm that's different than usual. So as I mentioned at the beginning, a lot of the images went into textbooks. But instead of just working with students, I'm interested in the general public at large and artists in particular. So I also work with artists, and this is a piece done with a new media artist. You can go to my website and play with it, move your mouse and play with it. And it's to give you the sense of how difficult it is in astronomy to look at objects and think that they're the same thing or different things and categorize them. And here you can see that what we do is quite different than public outreach images. So the artwork is quite different from the public outreach image. It's got different concepts behind it. And there's a new area that's developing called art science. And in those, the cultural object is supposed to have validity in both realms, in both art and in science. And one of the most obvious examples that's easy to grasp is the black hole in the movie Interstellar. That black hole was, the leader on that team was a physicist who imaged that black hole from the movie. So he understood the equations, and he worked with the theoretician who developed the equations. And the theoretician, while trying to deal with the imaging for the movie, would keep getting inspired and change his mind about what was going on in his theory of black holes. Does anybody remember who went to the lecture how many papers he wrote about that black hole? Something like 18 or I can't remember. A huge number of papers. So that black hole in Interstellar had validity in the science realm as well as in the cultural arts realm. And one of the other things I'm really interested in doing is incorporating audio, but I'm doing this with composers, new music composers, and I worked with an award-winning composer named Nikki Lizet. And we incorporated outreach images, but made it into quite a different cultural object that exists in the realm of art. And you can go and listen to the whole performance at my website, though you won't see all the video. Okay, time to do a recap of the talk. The culture of science has a very strong impact on the outreach images because they're made by scientists. They're the combinations of logic, tradition, data images. Okay, so it's data involved in it. So the public outreach images are an attempt to represent the science and not an attempt to represent what the eye would see. When you make a contour plot, you're not trying to make something that the eye would see. So when we're making the public outreach images, we don't feel obliged to do that either. And the public outreach images get used again in our professional journals. So we assign color to retain some scientific meaning or physical information so that they're useful that way. If you're not a research astronomer, say you're a citizen scientist or an artist, you can use them to emphasize an experience. We can use these to provide some insight into our science. What we often do is see things in these public outreach images that we didn't notice before. We want to test what's really going on, and we'll go off and acquire more data at different telescopes to try and prove something that's inspired by a public outreach image. But you can also use it if you do hobby astronomy to show the pleasure you experience when you're doing hobby astronomy. So I've been going around the world teaching people how to produce images in the image tradition using visual literacy, visual grammar, so that they can be very striking and really pique the interest of the public, inspire them to go and look up other material about those particular targets that they're interested in. but I don't consider the public outreach images on their own to be artworks. If you're a research astronomer, you want to limit the manipulation you do on these images so that everyone can trust the image. When they see a group of galaxies, they know it's really a group of galaxies and not a montage of galaxies. Zsolt Levay at the Hubble Space Telescope only likes to use techniques that are analogous to old film techniques, for example, dodging and burning, where you block some light. But of course, if you're a citizen scientist or an artist, you don't have to worry about that. And to finish up, I'd just like to say that sometimes I present this as if it's a battle, but if it is a battle between two sides, then the culture of science and the culture of art, both sides win in the production of making public outreach images. The last one here is just to show you that you can make very many different valid images that work from one set of data. This is the one I showed you from the Hubble Heritage Project. These three that I think are really good were made by students in my class. Okay, thank you for attending my lecture.